In previous videos, we talked about the advantages of three-phase power distribution systems. We looked at three-phase loads. In this video, we're going to be looking at three-phase transformers. Of course, it makes a lot of sense for power to be distributed over long distances at very high voltages. At high voltages, to deliver a fixed amount of power, less current has to pass through the wires. Less current means less resistive loss through the wires, and it also means that smaller diameter wires can be used. Therefore, it's typical at a power plant to have a step-up transformer, high voltage transmission lines, then a step-down transformer, and then lower voltages for distribution to customers. Finally, when power enters a residence or an apartment, it's at a low enough voltage as to not be deadly most of the time if somebody were to have an accidental shock. We've seen how single-phase transformers can be used to change low voltages into high voltages and back. But how is it set up when you have three phases? Do we have three-phase transformers? Well, that's what we're going to discuss here in this video. How can you arrange three different transformers or single three-phase transformers in order to do these voltage conversions when you have more than one phase? In this diagram, we're looking at a Y primary transformer. So we could think about the left side of this diagram as representing a power plant that is outputting three independent phases. We immediately want to convert the output of that power plant to a higher voltage. We want to step it up. And to do that, we're going to use a three-phase transformer. Now, this is a Y configuration. We're going to look at the delta configuration here in a moment, but I just wanted to point out that this transformer is clearly arranged in the Y configuration at the primary side. One of the advantages of using a Y configuration is that you can earth the star point. This can stabilize the grid. It's also possible to provide a neutral connection to the star point of the turbine as well. In this case, phase A, which comes out of this port of the transformer, is going to be in phase with the hot phase A that's coming out of the turbine. It just might be at a higher or a lower voltage. I think you can see from this plot that it's possible to use three single transformers and just arrange them in a Y configuration and effectively get a three-phase transformer. Now, practically speaking, with a three-phase transformer, sometimes they're wound on the same core material. But in this case, I'm showing it with three independent transformers. Either configuration is possible. Let's now take a look at a transformer with a delta primary. With a delta primary, there's no neutral connection, in this case, to the turbine. We just have the voltages across the delta. It's worth pointing out, though, that the voltage that shows up across any of these three phases is not going to be in phase with any of the three phases coming out of the Y at the turbine. It's going to be in between them. While this phase on this particular transformer core will be in phase with the primary side of that transformer, it's still going to be out of phase with any of the three phases coming out of the turbine. One of the features of having a delta transformer at the primary side is that the voltages are higher than they would be with a Y or a star connected transformer. Higher voltage means lower current if the power delivered is fixed. If you have a smaller current, then the wire diameter is smaller. If the wire diameter is smaller, then that can represent a cost savings. Or if the wire diameter is not smaller, then it means that there's less heating in the transformer. So when these transformers are used, these are some of the engineering considerations that go into deciding whether it's a Y or whether it's a delta configuration. Let's compare Y and delta transformers in this case. We're comparing Y and delta primaries here, but I'm also showing the secondary, so you could say that it's a Y transformer up here at the top, and down here at the bottom, you could call it a delta-delta transformer. Let's go ahead and draw in our neutral connection here for our Y-connected transformer. Of course, that's one of the advantages of having a Y-connected transformer, is that you do have the presence of a neutral. Neutrals are very useful in the sense that current can flow back through the neutral in the case that the loads are not balanced. You'll quite often see Y-connected transformers near consumer installations. So one residence might be using more power than another residence. You don't want the voltages to fluctuate to these two residences. Therefore, a Y-connected transformer connection would make sense. Let's put some numbers on these transformers. Let's assume that we have 10 kilovolts between any of the three phases and neutral. We're assuming that we have 10 kilovolts RMS here. If I were to take a voltmeter and measure the RMS voltage difference between, say, phase A and phase B, what would I get? Well, as you might recall, I just need to multiply my phase to neutral voltage times the square root of 3, and that will give me the phase to phase voltage. In this case, that works out to 17.32 kilovolts. That's exactly the voltage that would appear across the primary side of this delta-connected transformer down here. Now that we've calculated the voltages across the primary sides of these two transformers, let's write out a summary of the differences. We've already mentioned that the Y-connected transformer has a neutral and the delta doesn't. We've also just found that given a situation where we have the same phase voltages going to these transformers, the coil voltages are going to be higher in the delta case compared to the Y case. If we assume equal power flow to the loads in these two cases, it means that the current circulating in the primary coils is going to be different. Since power is related to the product of current and voltage, we know that a lower voltage then corresponds to a higher current. In the delta case, the higher voltage then corresponds to a lower current. Let's now consider what would happen if the load for each of these two configurations were hypothetically unbalanced. What would happen, for example, if the load on phase A has a different resistance than the load on phase B? Well, first of all, if we have the neutral present in the system, then if the load is unbalanced, then there would be current flowing in the neutral in order to balance out the currents. But if we don't have a neutral, it will cause the star point voltage to drift. If we have that neutral connection, then we're safe. Now let's think about the delta connection though. The voltage between any of the primaries of these transformers is fixed by the lines. So the voltage is not going to change, and that's one of the advantages of a delta transformer. If our load is unbalanced, the voltages are not going to drift. So we've looked at two different configurations, that is having a Y or having a delta at the primary side of a transformer. Let's now consider the secondary side of the transformer, and we're first going to look at the wye-wye configuration. Now this is one way of drawing it, but typically when three-phase transformers are drawn, the wiring gets a little bit complicated when we draw it like this. So we draw the transformer in a slightly different way. We simply separate on the drawing the secondary coil from the primary coil. Of course, with wye-wye transformers like this, it's common to have neutral lines as well in order to handle load imbalancing. That neutral connection will typically be connected to an earth ground at the star point of both the primary and the secondary of such a transformer. When we draw the coils apart like this, we also typically put a dot at corresponding sides of the coils to indicate how they should be aligned. Let's now take a look at a delta-delta transformer. Of course, some of the advantages of delta-delta transformers is that there's no phase displacement. The voltage that comes out of the secondary side of the transformer is going to be in phase with the voltage that you put on the primary side of the transformer. The phase A coming out of the secondary side of a delta-delta transformer, in other words, is in phase with phase A coming into the primary side. Delta transformers are good when you expect to have unbalanced loads because then the voltages aren't going to change. There's no neutral, so they also have advantages when it comes to power distribution. You can save wiring in that sense. Furthermore, because delta transformers have higher voltages for a given power flow, the current flowing through the coils tends to be less, and then it's possible to use smaller wires for a given amount of power flow. That's one of the advantages then of delta transformers. A negative, though, that goes along with that is that higher voltages typically mean that the electrical insulation around the wires needs to be a little bit thicker in order to prevent arcing inside the transformers. Another disadvantage of a delta-delta transformer is that neutrals are not available, so if you expect to have single phase loads that would normally need a neutral, then you wouldn't be able to use neutral at the secondary side. Of course, it's possible to mix these two types of transformers together. Here we're looking at a delta-wye transformer. This is actually a fairly common configuration. You can use the delta primary side when you have high voltages coming into the transformer and you don't have a neutral, so this would be common, say, in power distribution of fairly high voltages. Then we have a Y here at the secondary, which is good because we have a neutral that can serve out single-phase loads, and then the neutral allows the loads to be balanced. One of the negatives, though, of a delta-wye transformer is that there's a phase displacement. You'll notice here on the primary primary side that I've labeled the phases as A, B, and C, but I've not labeled them as A, B, and C over here on the secondary side, and that is because the output is not in phase with the input. There's a phase displacement. If it were a delta-delta transformer or if it were a wye-wye transformer, the output would be phase locked with the input. But here, the phases are going to lie in between the phases of the delta primary here at the output side. There are two main use cases of delta-wye transformers. First of all, this type of transformer is often used as the final step-down transformer for distribution to customers, simply because we get the neutral, which is important for load balancing. The second use case is for transmission at very high voltages. Delta-wye is often used for step-up. Since the voltages across all of the secondary coils are reduced by square root of 3 compared to what they would be if they were delta, this then saves insulation costs on the high voltage Y side. Then we have the wye-delta transformer, which can be used for step down from very high voltages for the same reason. The primary Y side has lower voltages across all the primary coils compared to the situation if it were delta, which means the primary side requires less insulation to prevent arcing. The secondary delta side current will be reduced by square root of 3 compared to what it would be if it were Y, so it saves on conductor sizing. Something to keep in mind is that with either wye-delta or delta-wye transformers, there'll be a phase displacement between the primary and secondary voltages. We're going to look at a few photographs of pole transformers, and you can find these in North America. Anytime you see 3 of these pole transformers together, that's an indication of a 3-phase transformer or 3-phase power. We're going to route some of these wires later and see how the transformers are hooked up. Transformers are usually mounted on a pole just below the primary side, and then we have the secondary cables mounted below the transformers themselves. Typically, when you have these electrical poles, the high voltage lines are on the top, the lower voltage lines are on the bottom, and the transformers sit in between them. The primary sides of these pole transformers would typically have more insulation, and they're usually called bushings. The secondary sides would then typically be at a lower voltage, and they would just be on the side of the cans. Let's take a closer look at one of these pole transformers and see how they're typically configured internally. From the photograph here, we can see 2 primary bushings, and we can see at least 2 secondary bushings. Primary bushings are usually labeled with the letter H. So here we have H1 and H2. The secondary connections on the transformer are usually labeled with the letter X. So you might have X1, X2, and sometimes X3. If there are 3 connections on the secondary side of these transformers, then the extra connection corresponds to having a center tap on the secondary side of the transformer. There are a few different configurations that 3 transformers can be hooked up to the primaries and secondaries: star-star, star-delta, delta-star, and delta-delta. I'll show you how to identify which configuration it is by looking at a pole. As I mentioned, the higher voltages are always at the top of the pole. You'll normally have 3 wires running parallel. There's sometimes a neutral wire way at the top of the pole. So if you sometimes see a pole that has 3 wires horizontally and then a single wire way up at the top wire is typically called a static wire, which is tied to neutral or earth. The reason why the neutrals are usually at the top is for lightning protection. If lightning were to hypothetically strike an electrical line, then it's better for it to strike something that's grounded, and then that current would flow safely down through an earth ground, rather than to strike one of the phases and then work its way back to transformers and cause fires and damage and things like that. If the pole's not too high, then there might not be a neutral at the top. Sometimes for Y-connected secondaries, if they're feeding these high voltage lines, then you might also have a neutral on the high side. The secondary wires will typically be insulated if they're very low to the ground, and the high voltage lines up at the top are normally bare aluminum. You can tell that they're high voltage if they don't have black colored insulation, for example, surrounding the wires. If they're insulated, then they're typically at a lower voltage, and you might sometimes see 3 or 4 of these wires. If you see 4, usually neutral is at the top. The 3 lower wires then would correspond to the 3 different phases. Let's look at an example of how these 3 transformers might be wired up in a star-star configuration. And the easiest way to tell if a transformer is connected in either the star or the delta configuration is to count the number of connections that the incoming or outgoing lines make with the transformer. If you see, for example, only 1 wire connecting one of the phases to the transformer, then it's going to be star. If you see more than one connection from the primary or the secondary side to its corresponding wires, then it's likely a delta configuration. In this case, because here we're showing the neutral connection on the high voltage side of the transformers, let's go ahead and draw the connections of the neutral bushings to the neutral on the primary side. What I'm not showing in these diagrams is the earth ground. Normally, the neutrals of the transformers will be tied to ground at the pole. Let's take a look at some poles that have three-phase transformers on them. When we look at these poles, we can identify the high voltage lines. There's one of the phases. There's one of the three phases, and there's the third phase on the primary side. We can see the connection that one of these phases makes with the primary side of that transformer, although the primary bushing is not really shown in this picture. What we have right here is a fuse. It's also called a cutout, and then we have a connection to the line. Again, for the second phase, we can see the line being tapped, then a fuse, and then there's a connection to the transformer that's not so easy to see. What's really clear about this set of transformers here is that we can see here from the third line only a single wire landing on that bushing on the primary side. So that's a clear indication that this is a star-connected transformer on the primary side. We can also see very clearly that the neutral bushings wind up in a star point here on the primary side as well. It's not so easy to see the secondary connections on that transformer, but it's easier to see them here on the next example. There's one of our three phases. There's another one of our three phases, and the third one is over here. It's not so clear how the primaries are connected, but I can see at least that power is being tapped at these 3 points and headed to the primary side of this transformer. Let's look at the secondary side. First, we can see our neutrals all coming up to a star point. It's an indication of having a star-connected transformer bank on the secondary side. It's also very clear that we have only one connection coming to the secondary on all three of these transformers. The primary connections aren't very clear from this photograph, but this transformer bank is clearly a star-connected transformer on the secondary side. We can summarize by saying that the left picture has a primary Y connection, and the photograph here on the right shows a transformer bank with a Y-connected secondary. Let's look at another example. In this particular photograph, both the left and the right images are of the same transformer bank. We're just seeing here a zoomed-in version so that we can get a closer look at how these wires are connected. There's one of our phases. There's our second phase. Over here is our third phase. These two wires down here are just helping to stabilize the pole. They're holding up the transformer, keeping it from tipping over. These are called guy wires. It's not so easy to see whether the primary side of this transformer bank is in the star-delta configuration, but we can clearly see the three cutouts, the fuses, on the primary side. If we look at the secondary side of these three transformers, we can see that it's definitely a star connection. I know that it's a star because each line makes only one connection to a transformer. There are three phases going out through the secondary, and we can very clearly see that the three neutrals are combined into a star configuration. The neutral line then here also goes down to the ground. It looks like in total we have 4 wires that go down through that conduit. Probably those 4 wires go underground and then serve a customer from there. We have a whole series of professionally filmed and edited videos in order to help students learn the fundamentals of electricity. If you like watching this particular video, then you might like to check out some of our others too.